Swayam Prabha. Digital India. Educated India.
Hello, good afternoon. Welcome to the course on comprehensive view of speech processing. So, today's class is lecture 15 in this course, and today we are going to discuss about different system representations, and among them we will try to focus on the pole zero representation, that is one of the system representations. So, these are the 5 different system representations where among these the top 2 we have already discussed, that is a time domain representation, and where in the time domain representation we have briefly discussed about a linear time invariant system where it is defined by the unit sample response, that is h of n, and x of n and y of n being the input and output of a system. So, the output response of a system, that is y of n, can be formulated as a convolution of the input signal with the unit sample response as a h of n. So, y of n is nothing but x of n convolution with h of n. So, that way we can able to analyze the system response for a given input, that is x of n, and with the unit sample response of a system h of n. So, for that we introduce a concept of convolution, and when you are discussing about convolution, we have seen how the convolution will be evaluated with the mathematical formulation with the given expression, and we also have seen that how these convolutions evaluated are observed in a graphical way with the graphical interpretation, that is convolution between the 2 sequences, how do we evaluate in a graphical manner. So, that we also discussed, and when you are discussing about convolution, very similar concept known to be correlation, even that also we have discussed. It is a very a simple difference between the convolution and correlation. In case of the correlation, where you can see in the formulation where which between the convolution and correlation, you can see that if y of n happens to be h of n convolution correlation, where you can see that summation of x of k into h of n minus k, and whereas in case of correlation, in place of h of n minus k, it happens to be h of n plus k. So, in a graphical way we can able to visualize the convolution correlation as, in case of convolution, one of the sequence will be flipped by 180 degrees and then it will be shifted like in a positive or negative direction. For every shift we will see the overlap between the 2 sequences, and that will be estimated as a convolution at a different shifts. And whereas in case of correlation, where out of the 2 sequences, one sequence will be fixed as maintained as static, whereas other sequence will be shifted without flipping in the positive or negative direction, and for every shift we will try to see the overlap area between these 2 sequences, that happens to be correlation for different shifts between the 2 sequences. And in the context of correlation, we also briefly discussed about autocorrelation, and we have seen that because when you are analyzing the speech signal basically contains during the voiced regions where you can able to observe the periodicity. So, from the speech signal, if we want to analyze or if we want to detect the periodic regions or periodic segments, so we can perform the autocorrelation, and then by observing or by analyzing the autocorrelation sequence or autocorrelation of the speech segments, we can able to detect or we can able to determine whether the segment is a periodic segment or not. If it is a periodic, it is a voiced segment. If it is a non-periodic, it is like non-voiced segment, or you can say that it is a silent segment and all. So, that way we discussed about the concept of convolution, correlation under the time domain representation. Then afterwards we discussed about the frequency domain representation. As I mentioned that because in time domain representation from the speech signal, you can able to visualize certain aspects or certain characteristics of a speech signal, like the amplitude envelope of a signal and periodicity of a signal and the energy of a signal at a various instance of time. So, from that we can able to detect where the speech is and where the speech is not present, and so these are the various things we can able to observe in the time domain representation. But there are certain things where like if you want to visualize the vocal tract system characteristics, right, where we need to analyze the system performance in the frequency domain. So, in that context, where for visualizing the signal or system in the frequency domain, so we need to use the Fourier transform, where with that the time domain signals will be transformed to frequency domain, and where you can able to see the frequency representations, or you can say that in a given signal or for a given system response. So, what are the various frequency components present and how the energy is distributed in the frequency components that are observed in a signal in the frequency domain. So, those aspects we can able to observe in the frequency domain, and that will be very useful in the context of a speech. What we have seen when you are discussing about acoustic phonetics of various sounds. So, each sound has very unique characteristics based on the shape of the vocal tract and the positions of the various vocal organs or articulators that are participated in the production of speech. So, different units. So, therefore, it is very important to visualize the speech, or if you want to analyze the speech in frequency domain. So, for doing that we need to evaluate the Fourier transform, or we need to perform the Fourier transform on the speech segments, so that we can able to observe the spectral characteristics or frequency domain characteristics of the speech segments and all. So, for that we can use the Fourier transform, but as I mentioned, since we have processed these speech signals by machine, by a computer, where it cannot handle the analog signals. So, therefore, we need to convert the signals to the discrete, and afterwards we need to quantize that, and we need to, for analyzing the frequency domain, both the time domain both the signal as well as its a spectrum, both should be available in a discrete and a finite duration, and finite amplitudes are required. So, in view of that, where the discrete Fourier transform will carry out the desired task of computing the spectrum for the given speech segment, and so for that we observe the various Fourier transform relations in a continuous time, discrete time, and discrete Fourier transform relations we have observed. And for performing the discrete Fourier transform, we have observed that what is the actual true signal and its corresponding spectrum, natural spectrum, and the moment once you want to use the discrete Fourier transform. So, what are the various trade-offs, what are the various approximations, or the operations that are performed on a signal in various steps. So, for each operation, what will be the loss of the information, and all those aspects we discussed graphically. And finally, we observed that in the discrete Fourier transform, by applying discrete Fourier transform relations, where your time domain signal and as well as its corresponding spectrum both are discrete and a finite duration, with which you can able to handle by a machine. And so, then afterwards the another way of representation of a system is the Z transform representation, and here the system is represented by H of Z, and X of Z and Y of Z are nothing but the input signal in Z transform and output signal in Z transform, and this H of Z is related to X of Z and Y of Z as the Y of Z divided by X of Z provides you the H of Z. That is nothing but a system transfer function and all. And here the H of Z representation is a very compact representation, mainly for implementation of the system. Suppose we want to design a system and we want to implement with the appropriate hardware components, the appropriate filters and the systems, where the Z domain representation of a system is more convenient and more accurate and more like optimally you can able to design the systems and all. So, that way the Z transform representation will be more useful at a stage where if you want to implement the system with the hardware components, or we want to develop a system at that point of a time, the Z transform representations will be very much useful. And the other way of representation of a system is the discrete equation representation, where in the discrete equation representation, where we relate the output, the present output with the previous outputs and the present and previous inputs. So, like here we will see that here the previous output and previous inputs, so they are weighted by various coefficients known to be the weighting factors like A case and B case. So, with the help of A case and B case, we will weight the previous outputs and the previous inputs as well as the present input. We will scale them with appropriate scaling factors. So, with that the present output can be estimated very accurately or more close to the actual output. And so, for that purpose we will represent the system in the form of a set of coefficients known to be A case and B case, and by optimally choosing or by optimally designing this A case and B case, these are going to be parameters of a system, where A case and B case, if you optimally choose or optimally design them, then the system you can able to predict the output more accurately or close to the actual output of a system. And the another form of representation of a system is a pole zero representation, and here the pole zero representation is nothing but, for this purpose we use a jet transform notation, but here we analyze the system transfer function h of z, where h of z is nothing but y of z by x of z, and it is nothing but y of z is the polynomials in the output, and x of z is nothing but the polynomial corresponds to the input. So, we will see that how do we derive these h of z in the next slide. These things we have discussed in the last class, and now we will see how do we derive the h of z from the linear difference equations, right. So, let us see. Before that, just I want to introduce the basic definitions of jet transform. So, this is the formulation or expression to compute the jet transform for the given discrete sequence. X of n is a discrete sequence over here, and by knowing x of n, we can able to compute the jet transform of the given sequence, as x of z is nothing but summation of x of n over the limits n minus infinity to plus infinity z power minus n, and where here the z is nothing but r into e power j omega, because as I mentioned the jet transform is nothing but it is a complex domain. So, where z is equals to r into e power j omega, it is a polar notation, where r indicates the distance from the origin in the complex plane, where r is the radial distance from the origin, and omega indicates the angle of a point. That means here first for the point will connect to the pole, will connect to the origin, and then that particular radial line, what will be the angle that with the horizontal line with the real axis, that indicates the omega, that is angle of the orientation of a given point in a jet plane, that is omega, that indicates the omega. Like the point will be represented by r into e power j omega. We will see that how, otherwise in the next slide it may be, here you can see here. Suppose here we have a point, for example, and so if you connect this point to the origin, so this distance indicates r, and then so this after connecting the point to the origin and this radial line, so the angle it makes with the real axis, this gives you this is the omega, or the angle that is provided, the angle with respect to the real axis. So, that will be your w and all, right. So, likewise this is for this particular point, so this will be the w, and whereas for this point this will be the w and this is the r. So, this way for a given point in a jet plane you can represent a point as like r indicates the radial distance with respect to origin, and w or omega indicates the angle that was made with respect to the real axis. So, this way we can compute the jet transform for a given discrete sequence, and similarly we can also, by using the inverse transform relation, if x of z is given, then from that we can able to recover or we can able to compute x of n back, similar to the Fourier transform and inverse Fourier transform the same way. So, using appropriate expression you can able to, if x of z is known, and from that you can able to recover the discrete time sequence using the inverse Z transform, And here if you look at this x of z, it's in Z transform of the signal x of n, and in this Z transform if you evaluate the Z transform at r equals to 1, or because the Z transform is a complex plane, as we have seen, something like you can see the Z transform will be like, so this is a complex plane, right, and here in this, as I mentioned here, suppose a point Z over here, it is nothing but this is r. So, therefore, here in this Z plane, if you take r equals to 1, so this is the r, and if you make a circle with r equals to 1, and on this circle, over this circle, if you evaluate the Z transform, so that is nothing but equivalent to the DFT, that is a discrete Fourier transform of a given signal and all, discrete Fourier transform of a given signal. So, that way we can able to evaluate, you can see here the discrete Fourier transform of a given signal is nothing but, and here if you substitute here by knowing z equals to r into e power j omega. So, when you put r equals to 1 over here and substitute here, it is nothing but it is expression of discrete Fourier transform computation expression for a given the discrete sequence x of n, that is nothing but x of n into e power minus j omega n, because when you plug in r equals to 1, so then the z is nothing but r into e power j omega. So, x of n into r into e power j omega n here minus j omega n, and when you substitute r equals to 1, it becomes x of n into e power minus j omega n. So, it is nothing but the discrete transform, discrete Fourier transform for the given sequence x of n. So, that way x of z is nothing but this is a complete plane, whole plane. In the whole plane, if you evaluate the Z transform on the unit circle, that is where r equals to 1, it becomes, it is nothing but it is equivalent to the discrete Fourier transform, Then the next one is the system representation using linear difference equations. So, here as I mentioned that in case of linear difference equations, the system is represented by a set of coefficients. Your x of n is your input and y of n will be output, and here the y of n is related to the input and the this previous outputs by using these parameters, the scaling factors a k and b k. Here we can write the output y of n in terms of the previous outputs and the present and previous inputs. So, here you can see, so y of n is we have written in the form of y of n as the previous history due to the outputs, that is y of n minus 1, y of n minus 2 and so on, y of n minus n. That means, we considered capital N the preceding outputs, and each output will be like weighted by coefficient, like y of n minus 1 is weighted by coefficient a1 and y of n minus 2 is weighted by a2, likewise y of n minus n is weighted by an. So, that way the present output or the nth instance of output depends on like we have here consider the history of n previous preceding outputs and the present input, that is x of n is the present input and we are estimating y of n. So, b naught will be the weighting factor for x of n and b1, b2, b3 or so on are the weighting factors associated to the previous the previous input and the previous to previous input and so on. And here our objective is that, so if we want to design a system, we need to design these AKs, right, this A1, A2, A3, AN and B case, B naught, B1, B2, BM. So, we need to estimate these weighting factors such a way that, so the output will be predicted very close to the actual one, because based on these the preceding outputs and present and preceding inputs, by appropriately scaling them, we can able to estimate the present input, the present output. So, y of n is nothing but the current output at the nth instant, and this is estimated based on the previous outputs and the present and previous inputs. So, for that we are giving different weighting factors or scaling factors for each of these components, and in case of designing the system here we need to estimate these parameters such a way that, so the estimated output, right, so that will be very close to the actual output. So, if the difference between the estimated and the actual one, if they are very close or if they are very less, it means that the design of the system is more accurate and all. So, here in case of linear difference equations, so the objective is to, we have to design these parameters such a way that, so the estimated output or the prediction error is it should be minimized. And now from these linear difference equations, so if we apply Z transform, because we know that we can apply Z transform on a discrete sequence. So, these are the discrete sequences, because y of n is the discrete sequence and my x of n is the discrete sequence, and these are the delayed outputs and delayed inputs. So, if you apply a Z transform in it, and you can get the expression in the Z transform expression like this, because for y of n the Z transform is y of z, and for y of n minus 1 if you apply Z transform, so the Z transform output will be y of z into z power minus 1, y of z into z power minus 1, because these are the expressions. So, if you apply in the Z transform here, if you if it is x of n, this is x of z. Suppose in place of x of n, if it is x of n minus 1, if you plug in here x of n minus 1, and then if you try to compute the x of z for x of n minus 1, for Z transform for x of n minus 1, then you can able to get, if you rearrange the variables that are there inside, y x of n minus 1 into z power minus n, and if you choose n minus 1 equals to some other substitute, then that way you can able to get, for x of n minus 1 the Z transform is nothing but z power minus 1 into x of z, right. So, that way based on that, if you can able to compute the Z transform, if you apply Z transform on this expression, you will get y of n y of z, and then for a1 into y of n minus 1 is nothing but z power minus 1 into y of z. So, likewise if there is a delay and you have the, if you compute the Z transform, it becomes z power, the exponent is nothing but the delay that is offered. So, z power minus 2 into a2 y of z. So, likewise you will get a Z transform upon this expression. Then by rearranging the y of z and x of z, and then if you compute h of z is nothing but y of z by x of z, and for that if you look at here, you will get the y of z by x of z is nothing but you have a polynomial on the numerator and you have a polynomial on the denominator. You have a polynomial on the numerator and you have a polynomial on the denominator, right. So, that way as we have seen earlier, in case of pole zero representation, we represent the system in the form of in the Z transform, but here we will try to analyze the system transfer function, where it is output by input, that is Z transform of the output by Z transform of the input signal, right. So, when you do that, you will get a polynomial in the numerator and a polynomial in the denominator. So, we can able to approximate, we can able to represent this notation as h of z equals to bk into z power minus k, where k equals to 0 to m, and denominator will be ak into z power minus k, where k equals to 0 to n. And here this n indicates that here this is this n indicates here we considered the n previous outputs, and here whereas we consider the n previous inputs. So, y of z by x of z. So, therefore, we have a corresponding the polynomials in the numerator and denominator. And here in this polynomial, since it is a polynomial, so you can able to factorize these polynomials. You can able to factorize these polynomials. You will get the factors will be either the linear factors or a quadratic factors you will get. If you will get a linear factors, then the roots will be the real roots, and if it is a quadratic factors, and sometimes you may get the roots may be either real roots or a complex roots. So, therefore, by evaluating these expression, these polynomials, and if the coefficients are real, and here the scaling factors happens to be real. So, therefore, if the coefficients are real, then by solving the roots of this equation, the roots may be either real or either complex conjugates, either real or complex conjugates. So, we will try to analyze the roots of this expression, that is roots of these polynomials which are in the numerator and the polynomial that is there in the denominator. And here the roots of the polynomial that is there in the numerator, those roots are known to be the zeros of the system, and the roots of a polynomial that is in the denominator, it is known to be the poles of a transfer function, the poles of a system. Why? Here if you take a numerator polynomial and if you derive the roots of this polynomial at root locations, that means if you plug in the root at that for that particular factor, either it may be quadratic or maybe the linear factor, then this entire expression becomes 0. Entire polynomial leads to 0. So, it is nothing but 0 by other polynomial. So, it becomes a 0, that means h of z leads to 0. That means at the root locations, at the roots, at the positions of the roots, the h of z will be, the response of h of z is nothing but 0. So, therefore, the roots of this numerator polynomial are known to be zeros of the system, right, and whereas the roots of a denominator polynomial are known to be poles of a system. Pole means actually it is like normally the physical thing, pole, where it is nothing but a sudden peak point, right, a highest point, it is known to be pole in a normal physical world, physical representation. So, therefore, here at the roots of the denominator polynomial, where the system transfer function reaches to infinity, suppose shoots up to infinity, because here at the roots of the denominator polynomial, the denominator polynomial responds to, or it provides 0 in the denominator. So, like in the denominator 0, then the h of z tries to shoots up the performance to infinite. So, therefore, the root locations or the roots of the denominator polynomial known to be the poles of a system, whereas the roots of a numerator polynomial of h of z known to be zeros of a system and all, zeros of a system. And here if you look at, for example, in this particular system, suppose for example, if all ak's are zeros, for example, if all ak's are zeros, then the system contains only the zeros, the system contains only the numerator polynomial, and with that you can say that it is known to be algebra system. It is known to be, because the if all ak's are zeros, right, here the a naught will be 1. So, therefore, even though all ak's are zeros, the denominator will be remains unity. So, therefore, the h of z is nothing but only numerator polynomial. So, the numerator polynomial will provide the zeros of the system. So, it is known to be algebra system. And whereas the other way, suppose the bk's are zeros, then it leads to only the polynomial in the denominator, then it is known to be all pole system and all. It is known to be all pole system. Otherwise, other than that, if ak's and bk's both are present, it is known to be pole zero system and all. It is known to be pole zero system. And here these poles will provide you these poles are indication of providing the resonances in the system and all. These poles are used to provide the resonances of the system, whereas in the context of a speech, a pair of poles or a pair of complex conjugate poles, they provide the resonances are known to be formats of a system and all, right. And whereas the zeros, if you have a zeros that are placed as a complex conjugates, so the zeros of a system will provide the anti-resonances of the system. That means, for example, suppose when you are producing nasal sounds, for example, through nasal cavity the resonances will be observed, but there is some energy that will be trapped in the vocal tract system or in the oral cavity, where it is not emitted at all. So, that entire energy will be trapped by the oral cavity, but there are resonances, but those resonances are not emitted out. So, those resonances acts as the anti-resonances are known to be the zeros of a system and all, zeros of a system. Likewise, even if you are producing a normal sounds like E or A, such certain sounds, where the vocal tract or the oral cavity itself will be divided into two parts, almost like very close to approximately, it divides into two parts. There is a frontal cavity with which the resonances will be observed or emitted out, and there is the cavity that is backside of the articulator. So, it is like whatever the resonances that are produced at the backside of a cavity, they will be simply absorbed. There is no way to emit those resonances, and those resonances acts as a anti-resonances or zeros of a system and all. So, that way we can analyze the speech production mechanism or the production of different sound units based on these poles and zeros of a system and all, right. In case of a nasals, we have both poles and zeros, and in case of a vowels, mostly where the vocal tract is completely opened. So, in that case, it is mostly the system is very much dominated by the resonances, complete resonances, and there is no anti-resonances. That means there is no energy trapped inside the oral cavity. So, therefore, the system can be approximated as all pole system and all. And if you observe that most of the sound units are like they are produced by the dominant resonances. So, therefore, in the case of speech, instead of approximating the system as pole zero system, so for the sake of simplicity, we will approximate the system as all pole system and all, because in case of all pole system is the numerator polynomial will be considered as like all the coefficients are zeros. So, therefore, we will consider only the denominator polynomial, then this approximation or the analysis of the system will be somewhat simpler and easy also. Otherwise, if you consider both the polynomials, and it will be complex, the system is complex, and basically analysis will be becomes more complex, because we need to see what are the resonances, what are the anti-resonances, and the interaction between those resonances offered by oral cavity, nasal cavity, that is between the resonances and anti-resonances, that will be tougher and all. So, therefore, for sake of easy analysis, we consider for a speech analysis purpose, we consider the transfer function of a system or our speech production system as an approximation to all pole system and all. But it is not accurate, because of this all pole system, we cannot model the anti-resonances or we cannot model the zeros at all. So, we are assuming that there is no zeros at all, but that is not true. So, that is the approximation we are making in the analysis of speech. And then coming to the in the analysis of pole zero system. So, once you compute the, like for example, for the approximation, the numerator polynomial, the coefficients of BKs are 0 for example, then it becomes all pole system. And if you solve this system, all pole system, because if the coefficients are real, the roots will be either real roots or complex conjugates, either real roots or complex conjugates. So, we will get a real roots from the linear factors, and you will get a complex conjugate roots from the quadratic expression or quadratic polynomial. That means by solving a quadratic polynomial, sometimes you may get a real roots and sometimes you may get a complex conjugate, that depending upon the discriminant value. So, therefore, here we will try to analyze the poles of a system transfer function, right. And so, if you analyze the poles of a transfer function, suppose when you if you get a factors. So, if you solve the factors, as I mentioned, that if the coefficients are real, you will get either real roots or a complex roots, and if at all if the roots are complex, then we will get the complex roots appear like complex conjugates. That means you will get a pair of roots, you will get always you will get a pair of roots, because ultimately you have to get the real coefficients. So, from the real coefficients you will get a real root, or otherwise if the roots are not real, then if it is complex, then to get a real coefficients back, here these complex roots are happens to be paired and they are complex conjugates, they are complex conjugates. So, therefore, you can able to see here a complex conjugate, a pair of complex conjugates here and a pair of complex conjugates over here. And if you try to like derive the roots, you can able to see that, as I mentioned, those roots will be placed in the Z plane, right. And those are, suppose for example, you have a pair of roots, complex conjugate roots corresponds to this one and its mirror image this one. Similarly, this is one of the complex conjugate and its corresponding conjugate will be here, the mirror image of that one, right. So, now these roots will be indicated by, like as I mentioned, that here this point will be indicated by r into like the e power j omega, where r indicates the radial distance of the root from its origin, and omega indicates the frequency. The omega indicates its angular frequency. It indicates what is the frequency of the resonance. What is the resonant frequency that is offered by the root? Here there are complex conjugate pairs, and here the omega 1 is the angular frequency that is offered. So from this omega 1 is nothing but 2 pi f t, where t is the period and f is the frequency of oscillation or the resonant frequency. So that way here the angular position or this angular this angle omega dictates or indicates what is the frequency of oscillation, and the radial distance of the root from its origin, it consists of r is nothing but e power minus pi bt, where b is nothing but the bandwidth of the offered by the complex conjugates, the bandwidth offered by the complex conjugate, because the complex conjugate pair, a pair of poles that will offer a complex conjugate that will give you like a frequency, the angular frequency, and we will see that how the roots look like and all. So here this r indicates the bandwidth offered by the frequency of oscillation, and where omega provides what will be the frequency, and as omega increases then the frequency will be increased, and if the root is a real, then the frequency will be 0. You don't observe any oscillations at all. The system response will be slowly died out without any oscillations at all, slowly exponentially died out. We will see that. Yeah, here you can see, as I mentioned, the poles and zeros of a system, and for example these are the pair of poles in a complex plane, they are the complex conjugates, and here r is the radial distance and omega is the angle offered by the pole, and from the omega you can able to compute the f, what is the frequency of oscillation, and from the r you can able to estimate what is the bandwidth and all. And for example, if there are two pairs of poles, this is one pair of pole, and if there is another pair of pole somewhere here and here, right, and a pair of pole here, these pair of poles offer a frequency of 1, for example here the black one, and another pair of poles somewhere here, right, where the angle is more than this one, and that will offer another frequency here like this, right. So that way each pair of poles will provide you the one frequency, that means the one format, and here as I mentioned, the distance of this pole from this origin, it indicates what is the bandwidth that is offered by the particular pole or the particular this one, the root, right. Here the bandwidth is nothing but, suppose the bandwidth is less, it indicates that the peak is sharper, that means the resonant frequency that is offered will be very sharp. It means the energy will be concentrated with a very smaller range of frequency around f1, and if the bandwidth is large, means here that means this peak is not sharper, the peak is somewhat flatter. So therefore the peakiness of the this format, or you can say that the width or the frequency range at the f1, that is indicated by the bandwidth, and this f1 this indicates basically the frequency. If the angular, if so there are other pair of pairs here, means that means there the angle that is provided by that pairs will be more, so therefore the frequency will be more. That means the red one is corresponds to the formats or the frequencies offered by another pair of poles somewhere over here, another pair of poles, because here if you join this and you can able to see that the angle that is offered will be more. So correspondingly the frequency that is produced by that particular pair of poles will be more. So that way you can able to analyze the frequencies, that is the resonant frequencies that is offered by the poles, a pair of complex conjugates, right. And in the time domain you can able to see this way, right. In time domain the frequency that is offered will be kind of a damped sinusoidal. You can see that this is a damped sinusoidal. So the sinusoidal frequency is indicated by this one, the angle, and the damping, the amount of a damping, that is indicated by the beta, that is r. That was r. That r that indicates the bandwidth and all, like the bandwidth or the amount of decay, how fast they will reach to very insignificant values and all, right. So this way we can able to, once we know the poles, or you can say the roots of a denominator polynomial, you can able to estimate how the frequency response used to be. You can able to see the frequencies offered by those poles. In a time domain it looks like this, and in the frequency domain if you analyze that, you can see that each pair of complex conjugates will offer you one formant frequency and all, one formant frequency. And these are the cases, if the poles are available as a complex conjugates, then you will get a formant frequencies, you will get a proper formant frequency that you can able to observe it. Yeah, that is the same thing whatever I mentioned over here earlier and all. You can see there are two pairs of poles, one pair of a pole where the formant frequency is equal to f1. If you look at the time period of that that particular response in a time domain, will be, this is the period t1 and it is nothing but 1 by f1. Whereas another one which is having higher frequency, where you can see the time period is nothing but 1 by f2, because f2 was larger. So, therefore, the reciprocal of that, the time period will be smaller, we have more oscillations. And next one is that we try to analyze that the radial distance offered by the poles, the radial distance offered by. So, if you look at here just for the analysis, you have different pairs of complex conjugate pairs, all of them have the same angle, all of them have the same angle. It means that all of them will provide the same frequency, right, same resonant frequency, but you can see that the radial distance offered by the different conjugate pairs will be different. There are some poles pairs which are close to the origin and some of them which are away from the origin, and there are some of them which are on the unit circle and some of them are outside the unit circle, outside the unit circle. And here if you look at here plot, so as the poles are like moving towards the origin, then you can see that the formant frequency appears to be more flatter. You can see here. So, suppose for example R3, you can see it is a more sharper one. Then R2, if you look at here, it is slightly less sharper, and if you look at R1, it's much less sharper, it's almost like appears to be flat. If you look at R1, R2, R3, R1 is very close to the origin, R2 is slightly away, R3 is much slightly away, and if you look at R4, R4 is at the place of on the unit circle, on the unit circle. So, if it is pole is on the unit circle, you can able to see the bandwidth is almost like 0, the bandwidth is almost like 0, it is like impulsive, it is almost like impulsive. And again, if the poles are moving away, you will get again, but here the difference between the poles that are within a unit circle versus outside the unit circle will be, if the poles are within a unit circle, then we will say that the system is a minimum phase system. That means, in a system, if the poles and zeros, if all the roots of a polynomials, if they are within the unit circle, then we say the system is stable. Otherwise, if a poles and zeros are outside the unit circle, if some of them are outside the unit circle, then we will say that the system is unstable, because if the poles are outside the unit circle, then for them, if you look at the response, then the response will be like, it is not like damping, it is like anti-damping. That means there will be oscillations, but these oscillations strength, they keep on increasing. That means they do not converge at all. Whereas, if the oscillations are damping like this way, they initially we have more amplitude, and afterwards as it time progress, these oscillations will be reduced, the amplitude will reduce, and this almost like the system will be convergent, the system will be convergent. But if the oscillations are other way, they started here and they keep on growing with the rising exponential, so then the system becomes unstable. So, usually if the poles are outside the unit circle, they are out of phase. So, with that you can able to see that the oscillations will be keep on growing, then the system becomes unstable, systems become unstable. And the system, if the poles and zeros are within the unit circle, this is known to be minimum phase system, and the system is also stable, and if the poles and zeros are, all poles and zeros are outside the system, it is known to be like a non-minimum phase system and all, it is like a non-minimum phase system or max phase system. And if the poles are, some poles are inside and some of them are outside, it is known to be mixed phase system, because the poles and zeros that are within the unit circle, they will offer the minimum phase, that means they will offer the damping, but they tries to converge the system. Whereas the poles and zeros that are outside the unit circle, so they are responsible for growing sinusoidals, so therefore they try to pull the system towards unstable and all. So, it is a mixed phase system, right. And suppose for example, if the system has a pair of poles or pair of zeros which are on the unit circle, then it is not to be marginally stable. It means that it has a sinusoidals, but the sinusoidal will not grow or will not converge. they keep on continue the sinusoidal with the oscillations with the same amplitude throughout. So, then you say that the system is stable, marginally stable. It means within the limits the system is stable, because it is neither converging nor growing also, right. So, therefore, you can say the system is marginally stable, and these concepts are not new. These concepts are like you can able to analyze, can observe the similar concepts in case of continuous time system. If you analyze a Laplace transform, where the concept of the Z transform is nothing but Laplace transform, and where this unit circle is nothing but this complex axis, or you can say that this axis, and this within the unit circle, the space within the unit circle is nothing but the entire left hand side of this plane, and if the poles are zeros or whatever, if they move out of if the roots are within the in the left hand side of the plane, then it is known to be system is stable, and if they are on this vertical axis, they are known to be marginally stable, and if they go out of this or towards right, then system becomes unstable and all. So, the same concepts here in the discrete domain, and where here we use the Z transform, and where here we will make use of poles and zeros, and with the poles and zeros you can able to carry out the analysis and you can state that whether the system is stable or not. And here you can see that there are two things. One is that the angle that is posed by the complex conjugates, and second one is the radial distance. The angle indicates the frequency of oscillation, and the radial distance indicates the sharpness or bandwidth, and also indicates the damping nature of the sinusoidals. Yeah, another here the same thing whatever I have just mentioned. Here the time in the time domain, how those frequency of oscillations look like. So, that were provided here. You can see R1, R2, R3 and R4, where R1, R2, R3 are those are within the unit circle, and if you look at this R4 is outside the unit circle. So, if you look at R1, R2, R3, if you see the R1, you can see it is almost like you see that the amplitude is very less, and it tries to converge much faster. And when you see the R2 and R3, so it has a sinusoidals, and it will take more time to converge, right, but they will converge at some point of a time. But if you look at the R4, because of this R4, they offer because this is as there is the phase that offered by this R4 will be reciprocal to that of this R1, R2, R3, like out of phase. So, therefore, here they offer the sinusoidal, but because all of them will offer the sinusoidal frequency of the same frequency. That is the reason, because if you try to analyze the frequency that was offered by the complex conjugates of R1, here I have not shown the other part of it, a mirror image of this. Otherwise, R1 means it has its other complex conjugate will be similarly R2 also. So, here I have not shown that, but here if you look at R1, R2, R3, R4, all of them have the same frequency of oscillation, but this R1, R2, R3 they are damped sinusoidals. So, they will slowly damp and they will converge, and whereas R4 and all, it offers you the undamped or like over damped sinusoidal. So, therefore, it provides you the rising sinusoidal, growing sinusoidal. So, with that the system becomes unstable, right. And then and these are like as I mentioned R1, R2, R3, R4. If you look at here, this R1 means which is close to the pole, where it offers a larger bandwidth, right. And as the pole is moving away from this one, and it offers less band, that means the frequency range that is offered will be narrower and all. It means the energy will be more concentrated in very small range of frequencies around F1, so on. Likewise, R3 also. If you look at R4, it is very similar to that, but only thing is that the sinusoidal will be growing. And the next thing is that so far we discussed about the poles, complex conjugate poles, right. And the other sometimes if you solve the polynomial, it may offer the real poles also. It may offer the real poles. Suppose if it is a quadratic equation, the quadratic equation, if you solve it, sometimes you will get a real coefficients, right. And if the linear factors, however, they will give a real poles, the real roots. So, in case of real roots means the roots will be in this axis, the roots will be in the axis. Real roots means omega will be 0, the real root, because the root will be indicated by Z, there is r into e power j omega, and if the roots are real means, that means the angular frequency is 0. So, it means the roots will be present in this axis, and again if the real roots are within the unit circle, then again the system is stable. If the roots are outside the unit circle, then the system will be unstable. And as I mentioned that these roots are on the real axis, the frequency that is offered, the resonant frequency that is offered by these roots are 0. So, that is the reason that if you analyze the real roots, where if you see that the roots are present on the real axis, and if you look at, if the root is close to the origin, that is a equals to 0, then here you can see that the bandwidth will be 0, and as the root is slightly moving away from the origin, then you can able to see that it is damping, right, and the damping will be reduced as the root is moving away from the origin, because you can able to find the highly damping when a equals to 0, that is if the root is at the origin, it is nothing but 0, it offers the 0, then immediately the system reaches to convergence. And if the root is away from the origin slightly, then if it is very close to the origin, then the damping will be faster and it reaches to the convergence state very faster. And as the root is moving away from the origin, then the damping will be less, it takes slightly more time. And when the root is in the unit circle, if the root is on a unit circle, it will not converge at all. Means at the same time it will not deconverge also. It maintains that means the system will maintain the root, that means you see the system response will be somewhat constant, and it will not come to the steady state, it will not come to the 0, that means, so it will be always constant, right. So, therefore, you can say that here the system is marginally stable, and at the same time the root is outside the unit circle, then it offers you the growing exponential. So, that system becomes unstable, and if the root is at infinite, then it is nothing but just suddenly shoots up, it becomes the system is unstable, and here the damping is very fast, it is a highly over damped system and all at very higher values of here. So, that way if you look at the roots, the real roots, where the response will be like this. If the roots are real, then the response of a system will be something like this. You can observe the system response will be like this if the roots are real, and this is a time domain response. And if you look at the frequency domain response, you can able to see like this. If the roots are real, you can able to see the frequency response is like this. The frequency response, or you can say the phase response, frequency response is like this. And suppose so far we discussed about the poles of a system, because the poles may have either real poles or a complex conjugate poles, and if it is a complex conjugate poles that offers the formant frequencies that is of our interest. Most of our speech sounds when they generate, the vocal rod system will resonate, and there are in the range of 0 to 4 kilohertz, there are 3 or 4 dominant frequencies will be observed, and most of the energy will be focused or concentrated only at those frequencies, right. So, that is the reason that here when you are analyzing the pole Euro system also, we will try to more focused on the poles of a system, and that too among the poles we will try to focus on complex conjugate poles, because they offer the the formants or formants with the different bandwidths, and from that we can able to analyze. And here the idea here is that by knowing the formants, right, so here we can able to make the system to be more flexible. Suppose for example, if I want to change the frequency, if I want to change the bandwidth, so then synthetically you can able to place the poles at appropriate locations, depending on our interest, we can able to synthesize the different sounds, right. So, here suppose if we want to have the formants should be, one formant should be at a lower frequency and another formant should be at a very higher frequency. Suppose we want to produce E, where the first formant will be very lower range and second formant will be very higher range. So, that way, and then accordingly we will set the bandwidths also. So, that way based on our interest we can able to set these poles at a different locations on the jet plane, and then with the collective effect of 3 or 4 pairs of complex conjugate roots we can able to synthesize the sound of our desired interest. So, likewise suppose for example what happens if you have a zeros. If you have a zeros of a system, for example, it means the zeros means they provide the anti-resonances, It means suppose for example you have a system, this is a jet plane, you have a zeros here somewhere here, if you have a zeros somewhere here, for example you have a zeros here, you have a zeros over here, it is a complex, there is a pair of zeros which are complex conjugates, right, and these zeros will offer anti-resonances. So, in case of anti-resonances the response will be something like this, It means that this is the frequency of oscillation here, this will offer a certain frequency. So, this is the frequency of oscillation and this is the bandwidth that is offer sharpness of this one, but here if you look at here, these are the zeros, that means at these pole locations the system tends to pull towards zero, towards zero response. So, therefore, if you analyze the h of omega or h of z, right, for a given pair of zeros, you can able to see the response will be something like, whereas here you can see the response will be poles, like at this particular frequency the system response will be peaks up or will be highlighted or the maximized, whereas here at the zero locations where you can able to see that the system response will be like pulled towards zero. So, that is the reason that these are also known to be the anti-resonances of the system and all, and if you actually design the system properly where a sound unit may be responsible with both zeros and poles and zeros, that means it has resonances as well as anti-resonances. In that case you need to design with a pole zero system and all. So, here with this we will stop this lecture and almost we complete the processing of speech signals, and in the next lecture we will focus on the speech analysis. Thank you.